Hi, everybody. My name is Skylar Larson, and I am an AAVSO ambassador. A little bit about me. I am an undergraduate freshman at MIT, right here. And currently, I am majoring in Earth, atmospheric, and planetary sciences with the planetary science track. I love planetary science and astronomy. Can't get enough of it. Currently, the vast majority of students at MIT have been scattered around the world due to the lockdown. But this gives my astronomy class, which is now online, a great opportunity to recreate an ancient experiment. And I would love to talk about that with you today. I have a presentation. Share my screen. That works. All right, so today I'm going to be talking about Eratosthenes and the circumference of the Earth. I looked up how to say Eratosthenes. I think I'm pronouncing it correctly, hopefully. Okay, so as like an intro question, when did humanity know that the Earth was round? Like based on your general history knowledge, can you think of it like a number, a year when like that was discovered or like come across? 1400s, early 1500s. Just like think of a number in your head that would be your best guess. And I have the answer. The ancient Greeks knew. We knew over 2,000 years ago that the Earth was round. In fact, there was an ancient experiment done by somebody named Eratosthenes that calculated the circumference of the Earth using nothing but sticks and trigonometry. A little bit of background on Eratosthenes of Cyrene. I'm vaguely certain that I'm pronouncing Eratosthenes right. I'm not sure about Cyrene. He was the person that did the experiment. He lived from 276 BC to 194 BC. He was the chief librarian at the Library of Alexandria for a time. So yeah, he's a very smart guy. Among many experiments that he did, one of the most important was accurately measuring the circumference of the Earth. I want to pause for a second on the word accurately. That's huge. Like to get something as huge as like the circumference of the Earth to reasonable accuracy in ancient times, that's kind of amazing. And I'm going to show you how he did it. Okay. So this experiment is like actually kind of simple once like you kind of understand it. Basically how he did it was that there were two ancient cities called Syene, again, not sure about pronunciation, and Alexandria. Fun fact, Syene is actually still a city. It's named differently, but it's still there. Eratosthenes knew that, the story goes that Eratosthenes knew about like this well in the city of Syene. You can see it on my mouse. It's like a little hole right there. Basically, he knew that on the summer solstice, light from the sun would shine inside that well and illuminate only the water at the bottom and like not the walls. So that's how he knew that the parallel light rays from the sun would go down and like hit the city like at exactly 90 degrees. That's how he knew, the story goes. Nowadays, we know that the city of Syene is actually really close to a latitude on the Earth called the Tropic of Cancer. It's basically as north as you can go to where the sun will still be like exactly up in the sky or at the zenith, as an astronomer would say. Knowing this, he also knew that the city of Alexandria was like, nowadays we know that it's not quite north of Syene, but it's pretty darn close. It's good enough for what he was doing. And on the same day, on the summer solstice, like light rays would not be exactly 90 degrees. Like let's say a pole in Alexandria would cast a shadow. It would cast a shadow. It would not be straight. The parallel light rays would not be straight down. Let's see. And if you can see in the diagram, what Eratosthenes wanted was to measure this angle right here, this A. That was the angle between the pole and the light rays coming from the sun. And I didn't already say this, but a really good assumption that this experiment makes is that the light rays are in fact parallel, just because the Earth and the sun are so far away. So the experiment goes that the sun is directly over the city of Syene on the summer solstice. A pole in Alexandria casts a shadow on the same day. So if we measure the height of the pole and the length of the shadow at the same time, like as the summer solstice shines on Cyan, we can calculate the circumference of the Earth using trigonometry. This is how we're going to do it, the math. Here we go. This is kind of like it's kind of a lot to take in, but I can, let's go through it step by step. The main, the data points that he took were the length of the pole and the length of the shadow. Through something called the law of sines, which for our purposes basically means that you have like a right triangle, you have two side lengths and an angle, you can find another angle. And in this case, we can use the law of sines to calculate that A that we found. So we find A, that angle between the light rays and the pole in Alexandria. And now we get to the point where we need to just know a few things about this particular experiment. Eratosthenes knew a few things. He knew the distance between Alexandria and Syene. And you can see the diagram here. It was about 5,000 stadia apart. A stadia is the kind of unit of measurement that the ancient Greeks used. It was supposed to be the length of a stadium, and I'll get to that unit of measurement later. But just know that it's kind of a unit of measurement that they use, kind of similar to kilometers or something that we would use today. So yeah, the distance between Alexandria and Syene is 5,000 stadia. And then he also knew that a circle goes 360 degrees around. So that's very important. So we know three things. We know the angle that we found, we observed the angle. We know the distance between Alexandria and Syene, and we know that a circle is 360 degrees around. We can use ratios to calculate the circumference of the Earth because we have two angles and a length, and we can find the other length. We have the circumference up here, 5,000 stadia at the bottom. These are the two lengths that one of the lengths is what we're trying to find, the other is what we have. And we have another ratio on the other side, and using cross multiplication, we can find that the circumference of the Earth is around 250,000 stadia, which is approximate to 39,690 kilometers. So this is really close to the actual circumference of the Earth, which we know today to be 40,075 kilometers. Eratosthenes was accurate to 1%. That's huge. That's huge for ancient times. There were some sources of error though, as there always are. There's, again, I'll get to the stadia now. There was an inconsistent unit of distance, which a stadia is supposed to be the length of a stadium, but also not all stadiums were the same length. A stadia wasn't a cemented known unit of measurement, kind of like a centimeter or a kilometer is today. Inconsistent units of measurement. And also, as I mentioned before, Alexandria is not exactly north of Syene. It's a little bit off, and that would affect calculations. But my astronomy class did this experiment. We're all scattered around the world, and so separately at our own houses, but at the same time, we decided on the time. I believe it was on a Tuesday a few weeks ago at 5 o'clock Eastern time, but 2 o'clock here. I'm in San Diego. We performed this experiment. Along with my sister, that's my sister / lab assistant, we calculated the length of this pole and the length of the shadow it casted at around, oh no, it was 2:15, around there. I think it was 2:15 or 5:15 Eastern Standard Time. That's right. We found a length of the shadow at the desired time. You can see my little setup here. I got a chair from the dining room table and my setup, got a ruler over there. But here are all the locations where the students did the experiment. I think I know the person who did this in Japan. She's a good friend of mine. Here I am in San Diego. We've got a Canada up here. A lot of people did this on the East Coast, some of them around Cambridge. And I mean, our math is a little different just because none of us are exactly north of another person. There's a few other things, and there's multiple measurements. But our final group measurement ended up being 40,169 with an error of 129 kilometers. This is good to less than 0.5%. So this is a relatively simple experiment for like what we're trying to calculate, but it's pretty darn accurate. And it's great that we can recreate this ancient experiment. All right, and I think that's all I've got for you. And I'm sure to come back with some other cool stuff, cool experiments. So thank you very much. I will see you next time.